All right, solubility. Let's draw your attention to the notes here on the screen and in front of you. If you have notes here in my class here. Glencoe, Text, Matter and Change, page 614, if you want to follow along in your text, chapter 17. Okay, so you probably have in front of you some notes with blanks in it, hopefully, so you can fill those in as we go through. It's a good way to follow along. And so I will try to highlight the blanks that you are filling in your notes to help keep you along. Where's my pen? Here it is. Okay. All right, so solubility. Some compounds readily, now first of all, readily is a fancy science term, mainly used in science. Readily reacts or readily dissolves. That means fairly easily and quickly, okay? So if some compounds readily, fairly easily dissolve in water. Okay, so dissolve is your first blank there. And some barely dissolve at all. All right? So if you think about something just very basic, like if you put a teaspoonful of iced tea into your glass of water and you stir it around, that's going to dissolve pretty quick, right? Or a pinch of salt, right? In the pot of water, you're making Kraft dinner or something, put a pinch of salt in there, boom, it's gone, right? Just as it hits the water, it's gone. It's not gone, it's in there, but it's dissolved into very small, tiny particles. And if you think about a rock, you grab a rock from the garden and you throw it in a pot of water, that does not dissolve very readily, right? So some compounds dissolve pretty easily and some barely dissolve at all. Table salt, as I mentioned, is a compound that dissolves easily in water. So table salt is that next line there, blank. You could also say that a lot of it can dissolve in a very little amount of water. So iced tea, let's say, you could make a pretty sweet glass of iced tea, right? You can put spoonfuls and spoonfuls in there. There will come a point where you can't dissolve anymore. You stir and stir and stir, and you can't dissolve anymore. And that's obviously, you've reached the maximum solubility of that iced tea in that amount of water. But you can understand how some things dissolve easily and some don't dissolve very much at all. So if a lot of it could dissolve in a little amount of water, this means that it is very soluble. All right, so it's important to understand how we use that term soluble. Some other compounds do not dissolve very easily in water under similar conditions. Okay, so compounds do not dissolve easily. These compounds are said to be fairly insoluble. So we have soluble and insoluble. Don't say not soluble, although that's not incorrect, but the term is insoluble. Not soluble is okay, that's two words. The one word is insoluble. It is insoluble, okay? These substances remain as solid and very little dissolve. So think about iced tea mix, think about salt versus a rock or magnesium carbonate from the lab or something. You're going to have a tough time dissolving that, and we're going to get into the lab hopefully here soon, and you'll be able to do a solubility reaction lab here where you can see that sort of thing. All right, so the measure of how much something dissolves is called solubility. So we take this word soluble and we turn it into this word solubility, and that is the measure to which something how easily it dissolves. So if something has a high solubility, that means it dissolves pretty easily. At a certain point, equilibrium will be established with the solid and its ions. In the example of NaCl, let's take a look at that. So another thing you need to understand too is what is a dissociation equation. Dissociation with the, I guess there's another blank here for you. There we go, solid. So dissociation equation, if I ask you for a dissociation equation, what I mean is, hey, write the salt, okay, in its salt form. So remember, S is salt form. AQ, now AQ, you haven't seen much of before, but that means aqueous. That means simply dissolved in a water solution, okay? It's dissolved. So it's not a solid. It's not a liquid per se. It's mixed up with water, okay? That's what aqueous means. So this is the dissociation. It's splitting apart Na and Cl into its constituent ions, okay? It's not reacting with anything. This is not a chemical reaction. This is a physical sort of change. This dissolving is simply taking something and pulling it apart. We're not rebonding with anything else. There's no new product formed in a sense that Na and Cl are the same elements that existed before. Okay? So this is a dissociation equation. Decomposition is another, decomposition would be another sort of name, but it's not the same because that's, we're creating, we actually have brand new products because the atoms are arranged just slightly differently in decomposition, in many decomposition reactions. So this is dissociation into its ions mixed in with water. All right. The phase equilibrium equation represents the point at which the solid is dissolving and ions are reforming solid at the same rate. So this is just like equilibrium. We just got finished talking about equilibrium. The phase equilibrium equation. So at the point which the solid is dissolving and ions are reforming the solid at the same rate, just like equilibrium. So here's all your blanks that you should fill in for your complete notes. And it looks like this. So we have NaCl, solid, and here's now where we put our double arrows, right? So this is the dissociation. This is now the phase equilibrium. And it's called phase equilibrium because we're talking about a solid phase versus an aqueous phase of the same substance, okay? It's called phase equilibrium. You guys all with me so far here? Yeah. Any questions, just throw up your hand or whatever. Let me know if you have any questions. I'll pause and answer your questions. Pretty basic so far, just learning some basic terms and that. All right, so we just finished studying equilibrium, as I mentioned. So if you treat dissolving as a phase equilibrium, one could write the equilibrium constant equation. So one could write an equivalent sort of equilibrium constant equation. Studying equilibrium. Yeah, it would look like this. Okay, so the KEQ for this reversible reaction at equilibrium, okay, the KEQ expression would look like this. We would have the concentration of the products multiplied together. So the products, I'll put that in air quotes, Na plus concentration times Cl minus concentration, all with exponents of 1 because we have a 1-to-1-to-1 ratio, divided by, and now here's where it seems a bit funny, but in the equilibrium concentration, equilibrium expression, we would have the concentration of NaCl, solid. But as you remember from our study in equilibrium, the concentration of a solid is always constant. So that's the only issue here. So what is different here is that we have the concentration of NaCl. It's a constant because it's a solid. So where is that in your note? It is constant because NaCl is a solid. So remember that solids are not included in the, for example, the ice charts, as well we just got finished learning about. So solids are not included because their concentrations don't change at equilibrium or going to equilibrium. Okay, so do you have everything there? Okay, because adding more solid doesn't change its, and then here's your last blank on that page, okay? So rearranging things a little bit there, if we brought up this NaCl solid concentration, like in air quotes, if we brought that up here, then what we would have is we would have the traditional sort of KEQ value for this times the concentration of a solid, which wouldn't change. So really, if you take a look at these two things right here, we really have a new constant, okay? We have a new constant because both of these would technically be constant. The only thing that would change would be the concentrations here of the ions. So in fact, we do have another constant in the KEQ expression, and this gives us another type of solubility constant. This is actually called the solubility product constant. Similar to the equilibrium constant, but it's the solubility product constant. And the notation there is KSP right here. So K with a little SP instead of K with a little EQ, right? Not equilibrium constant, but it's the solubility product constant. So just as a refresher, this KSP really is the same as what the traditional KEQ would be times this constant of a concentration of solid that's involved. And so that's our new KSP. So notice that the solid, the amount of solid, is not included at all in the calculation for the solubility, which makes sense, I guess, right? If we're talking about how much dissolves or what's the measure of the, the dissolving capability here of this substance, all you're really looking for is how many of the ions, how many of the broken pieces exist. And you can just use those numbers to calculate this expression, or this value. So what the solubility product constant tells us, I'm just trying to find my note, is the maximum product, and when I say product here, I'm talking about multiplication now, all right? There are products that are substances that are produced, but here I'm talking about the maximum product. I'm talking about multiplication here. So this is like a times, right, in between here, multiplication. So it's the maximum product of the concentration of dissolved ions in solution, dissolved ions in solution that can exist before those ions, and this is a good way to think about it. It's the maximum sort of an amount of individual ions that can exist before those ions start to bump into each other and reform the solid again. It gives us an upper limit. It gives us an upper limit to the concentration of ions that can exist individually before they bump into each other and form the solid compound again. Okay. So if I have, a solid and it's going to dissolve, let's say, into its individual pieces here, that's great. But the more we have in solution, if we have a whole bunch of these all dissolving, then we've got a whole bunch of these little particles and big particles and all that. And so if there's enough of them, right, what's going to happen is they're going to start bumping into each other, and they're going to start reforming the solid again. And so they're going to come back this way, and that's where we get our equilibrium. Okay? So we've got individual particles, yes, but they are now sort of coalescing back into the solid. And think about your iced tea, right? If you have a whole ton of iced tea in a glass of water, there's always little crystals at the bottom. And if you could zoom in and magnify in to the sort of molecular level, you would see these crystals sort of splitting apart and going up into the glass solution that you drink. And you would see other particles sort of like coming together and falling out at the same rate, sort of thing. So a substance is highly soluble. A substance that is highly soluble will have many ions in solution. Will have many ions in solution. This gives us a very large KSP. So as I mentioned, a large KSP means something is very highly soluble, which means that there are lots of these things individually in solution before they start getting back together. Something that's insoluble, right? Let's say you have something like this, and what happens is literally there are just far fewer individual little pieces, and it doesn't take much, and these guys just really want to get back together into the solid, so it very few in solution if it's rather insoluble. So that's just noted here. A substance that is considered fairly insoluble will have a low KSP for the same reason. The product of ions is low. Okay, have I fairly clearly laid this out? I think it's a pretty basic concept. We've learned a few terms, the basic idea for solubility, okay? Now, if you want to turn to page 650 in your Glencoe text, it does give you a list of solubility product constants for a wide range of compounds, and really, compounds that are fairly insoluble are mostly the ones that you'll see in these charts. The ones that are super soluble will have really large KSPs, and they're not worth even mentioning because our calculations will be centered on substances that have lower KSPs. All right, so here's a chart similar to the one in your textbook. First of all, a couple things I want you to notice. Solubility product constants The data for them like this, the constants themselves, are usually given at 25 degrees Celsius, which is considered to be room temperature. So in a lab situation, usually the lab is, in room temperature. Labs are not always conducted at 0 degrees Celsius or, anything else. It's usually just at room comfortable temperature for the scientists that are doing the lab. So you'll see that, first of all, you'll see that. Now, you'll see that these numbers are fairly low for a lot of these compounds. And by fairly low, I mean that they have, these are written in scientific notation, as they are in your text. And when we have a very large negative number on the 10, you know that that's a very small number, right? So for example, this one here, manganese sulfide, okay, 7 times 10 to the negative 16, that says. So that's 0, decimal, and then 15 zeros ahead of the 7, right? So it's very, very small. Now, what does that mean? Well, if it's very, very small, okay, very, very small, that means that the product of ions in solution only needs to be very, very, very small, okay, in order for them to coalesce and get back together again. So the amount of ions in solution is extremely small. So manganese sulfide is very insoluble. It does not tolerate a lot of ions in solution, okay? Get that? So if there's lots of ions in solution, the numbers will be large. Now, barium hydroxide. So look at this one down here, barium hydroxide. Now, barium hydroxide is a base, and it is fairly soluble. Now, we still have negative numbers, but notice that this is 10 to the negative 3. And so generally, and I don't know if I think I have these in the notes somewhere. Yeah, so you don't have to write it down now maybe, but anyways, generally the cutoff is about 10 to the negative 4, okay? So anything higher than 10 to the negative 4 is considered soluble or fairly soluble. Anything that's above 1, right? 1, 5, 10, 20, 100, that's extremely soluble. It's like as soon as it touches water, it immediately dissolves, and you can fit a ton of this substance in there and they will all dissolve. There's lots of room. The ions are very tolerant to each other and they will not bump into each other and form solid again very easily. Highly soluble. But these numbers, a lot of them are very small. Look at this one. Hg is mercury, I is iodine, right? So what do we have? Mercury 1 iodide. And this is 4.5 times 10 to the negative 29. So there are virtually no ions, free ions in solution. Virtually none. Because the product only needs to be this extremely small number, and then boom, they're going to get together and form the solid again. So that's extremely insoluble. Got it? Barium hydroxide, fairly soluble. So anything up to 10 to the negative 5, fairly insoluble. Anything greater than 10 to the negative 5, like 10 to the negative 4, negative 3, 10 to the negative 2, 10 to the negative 1, those are fairly soluble. Okay? All right. And we are going to be, my plan is to do a solubility lab with you where we're actually going to dissolve certain amounts of ions. We're going to throw them into a solution together, and we're going to be able to predict which compound should form based on the solubility of all the ions that are present in the solution. And then you're going to collect that product, and you're going to analyze it a bit and do some other calculations. So solubility. All right. All right, let's continue on with the notes here. So at a certain temperature, and again, temperature affects equilibrium, temperature affects solubility big time. If you have a hot glass of water and you're making iced tea, well, it's not really iced tea if it's hot, but if you're making tea and you're dissolving iced tea crystals, a hot glass of water, you'll be able to get quite a bit sweeter. You'll be able to dissolve more ions in there. A very, very cold glass of water, you won't be able to dissolve as much, and you should try that sometime. You could even try that today. Have a nice cold glass of iced tea when you get home, and then put the kettle on, same amount of water, same number of teaspoons of iced tea, and see what the dissolving process looks like. See what happens. See if you can get more iced tea into the hot water. See if I'm lying to you. You should probably test that out, because there's a good chance I'm lying to you, right? That's what teachers do, right? No, that's not what teachers do. I'm just joking. But you should check that out. Where was we? Okay. I said where was we on purpose. Okay, Rob, you looked up at me. It's okay. I know it's not the way you say that. But not being an English teacher, I feel like I can get away with speaking, incorrectly sometimes. Because I learned English really well, really gooder. I'm gooder now than I ever was. All right, we'll axe that out of the video if I have time. At a certain temperature, the concentration of A plus is 0.02 molar, okay? So this is an example situation here. And the concentration of B minus is 0.3 molar. So you see where we're at there? Middle of page 2, guys, in your notes. If this is the maximum amount of ions that can exist in solution, so the maximum, without forming a solid, and that solid would be the combination of A plus and B minus, which would be AB, right, 1 to 1. According to this equation, if this is the maximum amount, then we have something called a saturated solution. Very important that you know that. Saturated. Saturated means everything is in there that it can possibly handle. Okay, there's not an excess of anything. It's completely saturated. All right. If you have a dish rag or you have a face cloth or something, you put a little bit of water in it, just on the face cloth there. It's a little bit damp, but you could put more on. So when you, I just said more on. You can put more on, more water in. Let's say that. So yeah. If you keep adding water to the cloth and nothing drips out, then you are not completely saturated yet. But as soon as you add one more drop of water and it's unable to hold it and now a drop comes out the bottom, then it's, you know that at that point it's completely saturated, right? Just like a glass of water. It's completely full when one more drop spills another drop out, sort of thing. Saturated. You can add more on. That's awesome. Okay. Also, the solubility product constant KSP can be calculated. So we have this number. We multiply them together according to the equation right here. Okay. So now it doesn't matter if the ions are on the left side or right side. Really doesn't matter so much here. But the product of the ions you would multiply. Now, we would keep in mind that if there was a 1-to-2 ratio of ions or something like that for some reason, then you would have to square, right? Okay, so you'd still have to do that. We'll keep that in mind from equilibrium. All right, so the KSP at this temperature for this fictitious compound AB would be 0.006. Now, there are no units for KSP. You notice on the chart there, there's no units, it's just a number. It's a product of the concentration of ions. We could figure out a number, but it's going to change for each compound because if we're squaring something or cubing something or not, technically the units would then change, right? Moles squared or moles cubed. So we don't include the units solubility product constant. What does this mean? Well, this means if we're understanding this, you should know this, that any product of concentrations of ions that are greater than this 0.006 will yield some solid AB in solution. So again, if we have any combination of concentrations of ions A and B where the product is greater than 0.006, we should expect some product in solution. All right, it's too full if the product is greater than 0.006 or 6 to the negative 3. All right, so what about your blanks here? This means any product of concentrations of these ions greater than 0.006 will yield some AB in solution, some solid. Any products of concentrations of these ions less than 0.006 will not yield solid AB in solution. All right, so also, this is now a little bit of a different example. You can calculate individual concentrations of ions if you are given the KSP. So let's say you're given the KSP of a certain compound at a certain temperature. What are the concentrations of this saturated solution? If it's saturated solution, well, you can go the other way. Instead of multiplying concentrations to get KSP, you can break down the KSP into the appropriate concentrations. Okay. Now it is going to depend on what the dissociation equation looks like. It's going to depend on the molar ratios of the ions and so on. So we'll have to pay attention to that. But in order to do this, what should you do? You should write the equilibrium equation, the phase equilibrium equation, or the dissociation equation. The only difference between the dissociation equation and the phase equilibrium is the double arrow in the equilibrium, right? So then what you're going to do is you're going to use a single variable to represent expressions for each ion. So and I'll do an example here, of course, but if you have a 1-to-1 ratio of unknown ions, they each can be X. They're the same, right? You're going to have the same number of moles and the same concentrations of each being produced. If one is a 2, well, then you're going to have double the concentration of this ion being formed, right? If it's a 1-to-2. So you have to keep in mind that. Write the KSP expression, including the values and the variables. Solve for the variable, and use that variable to determine concentrations. So your blanks are write the KSP expression, solve for the variable, and use the variable to determine concentrations. So here's an example. We good so far? You ready for this example? Okay. So again, we've calculated KSP by multiplying products of concentrations of ions, and now we're given KSP, we're going to go backward the other way. This is what it looks like. So given the KSP for BaCO3, this is barium carbonate, that number should be same as in your chart in your textbook, is 2.6 times 10 to the negative 9. That's the magic number that any product of ions of barium and carbonate, any product greater than that should form a solid in solution. Anything less, they'll stay ions. So what do we have? Find the concentrations of each ion in a saturated solution. So that's kind of the max, right? What's the max? What are the concentrations of ions that yield that particular KSP? Well, it's easy. So we're going to write the dissociation, sort of phase equilibrium expression. I see that because of this formula, it's 1 Ba to 1 carbonate. Wow, why did I do that? This should be a 2 plus, and that's obviously a 2 minus there. Right, okay, so I don't know why I missed that. I wrote it right way down there. Give me 1 second there, okay. And take you up top, good. Right, so barium is a 2 plus ion, carbonate 2 minus ion. You can fix that in your notes if it's not in there. Anyways. And so what we have is a 1-to-1 ratio, so each of them can be X. Okay, they both can be X, 1-to-1 ratio. 1-to-1. There's your blanks. Okay, so we know that now we just simply take the KSP expression, we fill in values or variables. So KSP is this, variables are X times X, that's X squared. In order to solve for X, you guys all know this, you do this when you're itty bitty babies, you just took the square root of both sides, okay? So you take the square root of both sides. Notice, when you take the square root of a very small number, right? The square root of a very small number, you're gonna get a bigger number, all right? And so don't be surprised, because when you square this bigger number, take the square root, you square a small number, you're going to get a smaller number, okay? So when you square root a small number, you're going to get a larger number. Anyways, just trust your calculator on that, but just know that these numbers are going to grow when you take the square root of a very small number, which will be the case most of the time in these calculations. So when we solve for X, we get X equals 5.09 times 10 to the negative 5, which means that these are the concentration, that's the concentrations of the ions in a saturated solution. They'll both be the same, because they break down to a 1-to-1 ratio. They'll both be the same. And your units, you do have to have units on concentrations, correct? And those units will yield moles per liter, capital M moles per liter. So the KSP doesn't have units, but your concentrations should have units, okay? Any questions? You guys with me here so far? Kind of following along in the textbook, perhaps? Sorry, this is kind of a little bit of a boring lecture. I don't have any fancy videos or diagrams for you here, but hopefully you're getting it. Questions, or are you good? Anybody? All right. Okay. So what does this also mean? This also means, okay, this also means that the solubility of BaCO3 at this temperature is 5.01 times 10 to the negative 5 molar. So when you hear that terminology, what's the solubility of barium carbonate? Well, you could take the KSP and find out what the what the value is that it would break. That's the maximum. So this would be the maximum sort of concentration of BaCO3 that would break down, right? It's the solubility. Okay. This is because all three substances in equilibrium are 1 to 1 to 1 in molar ratio. So like I say, if this was whatever your kind of base 1 is, if this is a 1, right, then we have a 1 to 1 to 1. So this number here, this concentration, okay, can be appropriated to this solid. I know that solid concentration, that's a bit funny, but this concentration is how much of this, moles per liter, that's what capital M is. So this many moles per liter at this temperature should dissolve, should fully dissolve, and that will give you a saturated solution. So the solubility also can be assigned to the constant that's dissolving. All right, so in your textbook here now, we're going to take a look at some example problems, and then there's going to be some text questions for you to do. On page 616 is where you want to go to look at sample problems. So page 616, example problem 5. These will set you up for the questions that you're going to be doing on that page. So it says this, calculating molar solubility. So use the KSP value to calculate the solubility in moles per liter of copper 2 carbonate at 298. Now remember, 298 is in kelvins, and 273 is 0 degrees Celsius, okay? And so 273 is 0, so add 25, you get 298, so this is room temperature. So 25 degrees Celsius or 298 Kelvin, that's just basic room temperature, with which most of these data points are calculated on. Okay, so first thing you want to do is analyze the problem. You've been given the solubility product constant. The copper and carbonate ion concentrations are in a 1-to-1 relationship, which we just did in our example, with the molar solubility of CO3. Okay, so again, if you look at, where is it? So look at this equation right here, the chemical equation, right? The ion concentrations are here and here, and this would represent the solubility, okay? So the solubility of the solid. So they're in a 1-to-1 ratio. That's great. So we can do everything that we've done before, knowing the KSP here. So we substitute the KSP, and that's this 2.5 times 10 to the negative 10, and then we're going to let a variable, either x, or in this case in the textbook they let Cu2 plus and CO3 2 minus equal s. So it's just x squared or s squared equals your KSP. Take the square root and you're done. All right, evaluate the answer. Does it look reasonable? Let's see, what do they say? The KSP value has 2 sig figs. So if you're wondering how many decimal places to go, check your initial measurements and go with the fewest number of sig figs. So the 2 digits, okay? And then the solubility there would be moles per liter of the solid. All right, so let me do 20A with you, just to make sure you're on the right track. I'll give you a chance to do the rest here. So use the data in table 3 to calculate the solubility, moles per liter, of the following ionic compounds. So I've got my text here. Textbook on, back up a couple pages there, or 1 page. So PbCrO4, okay, so PbCrO4, that's lead chromate there, 2.3 times 10 to the negative 13. Now, that's the KSP, that's not the solubility, right? The KSP is lead, so 2.3 times 10 to the negative 13, okay? All right, so let's write the phase equilibrium or the dissociation equation at least, right? So we have to find out what this looks like. Is it a 1-to-1 ratio or not? In this case, if you look at this, it looks like it's a 1-to-1 ratio with this lead ion and the chromate ion here. So what do we got? We've got in equilibrium with Pb, what's CrO4? 2 minus? Pretty sure, so 2 plus, and we're going to have CrO4, 2 2 minus, let's double check. Just double check that actually. I don't have any of the solutions here. Let me just double check that here for a second. All right, so those are all correct, yeah. So we have a 1 to 1 to 1 ratio. So this is going to be easy, just like the question that we just did there. And so we're going to have 2.3 times 10 to the negative 13 equals x squared, or use whatever variable you want. Take the square root of both sides, and then you should get your answer. And that x will be the concentration. The x will be the concentration of each ion in moles per liter. It will also be the solubility of the solid. Okay, so let's see, thank you. So the square root of 2.3, use your little scientific notation button there, negative 13. Square root is going to be 4.79583 times 10 to the negative 7. So we have 2 sig figs given, so let's just go to 2 sig figs. So that's 4.8 times 10 to the negative 7. So x equals 4.8 times 10 to the negative 7. So the question, remember, we're not just going to circle that and move on. We're going to, again, examine what the question's asking. Solubility in moles per liter. So the solubility will be 4.8 times 10 to the negative 7 moles per liter, okay, of PbCrO4. So that means at this temperature, this concentration of this solid, this concentration should fully dissolve. That would be the maximum point, okay? So go ahead and do the same thing for B and C. These are pretty easy because they're all 1 to 1 here, looks like. So this is pretty straightforward here. Get some practice. Also do number 21. Do number 21 as well, okay? Okay, so for question number 20, if you've had a chance to take a look at that, I'll mention just a couple things. One that I've mentioned already, somebody asked about this, but for B, okay, when you're writing the dissociation or the phase equilibrium, you do not have to apply the rule for the diatomic 7, okay? That's only if it's in strictly elemental form, not if it's in ionic. So for example, like H or Cl or Br, you don't have to automatically put a 2 there, a Cl2. When we're talking about just ions, we're talking about this exact compound here. When it splits up or dissolves, you get 1 Ag plus ion and 1 Cl minus ion. So that makes that pretty straightforward. B and C are exactly the same. Now for 21, you can check your answers for B and C there. For 21, the challenge part of it is this. What is the solubility in grams per liter? So the X value that you might get is going to be in what? Moles per liter, yeah. So you're going to have to change moles to grams. You have to think back to Physical Science 20. You're going to have to think back to early in this course when we converted moles to grams, right? You multiply by the grams per mole of the substance. So that's how you do 21, and I'll show you the answer to 21 here just in a minute here, give you a chance to work on that. So that's the catch here with 21. So once again, for 21, what you're going to need to do is you're going to need to find the solubility as we did with the other questions, but that solubility that you get will be in moles per liter. And so in order to determine the solubility in grams per liter, you're going to have to multiply that moles per liter times the molar mass of lead 2 carbonate. And on your periodic table, you find the molar mass of Pb. You add to that the molar mass of carbon, and then add to that 3 times the molar mass of oxygen, and you should get 267.2. Multiply those together, and this is the number that you get. So the solubility sometimes is in moles per liter, but sometimes it's in grams per liter. And you'll see for a lot of data charts, it will be the solubility will be in grams per liter instead of moles per liter. All right. Let's move on to the last and final sort of section of questions that we need to be able to work with here when dealing with KSP. And I'll zoom in. This is also in your textbook, Glencoe Matter and Change Science. This is on page 617 now. This is example problem 6. So what does this look like? Well, looks like this. We've got magnesium hydroxide, MgOH2. It's a white solid. It's obtained from seawater and it's used in the formulation of many medications, in particular those whose function is to neutralize excess stomach acid. Determine the hydroxide ion concentration in a saturated solution of MgOH2 at 298. And here's the KSP given right here, 5.6 times 10 to the negative 12. Okay, so analyze the problem. How are we going to do this? Well, we're going to do this very similar to how we did our other questions, but what you want to notice here is that we have a bit of a twist in that MgOH2, we've got, this is dissolving into 1 mole of Mg ions compared to 2 moles of OH ions. So that's going to change how we assign our variables, okay? So given the KSP here, what we have to understand is that the dissociation equation or this phase equilibrium equation here is going to be a little different. And how is it different? Well, we have a 1 to 1 to 2 molar ratio. That's going to be the big kicker right there. So if we're given the KSP, no problem. But what we have to understand is that 1 mole of this substance produces 1 mole here. So I'm going to let this be X. But it also produces 2 moles of this ion. So this has to be 2X. So if you look down here, the KSP comes from, okay, the KSP expression right here has a 2 as an exponent on the OH because of this coefficient there. So remember from the KEQ lesson, right? So the KSP is the concentration of magnesium to the power of 1 times the concentration of OH minus to the power of 2. So yes, it looks a little strange, but yes, you have to use 2x and you have to square it. So it's 2x squared. It's not one or the other, it is both. And my students always kind of say, well, that seems strange. Why are we doubling it and squaring it? Well, that's the way this KSP is built. That's the way we have to decompose it now. So what that turns out to be is 4x cubed equals your KSP. To solve for x, you would do 2 steps here. You would divide by 4, and then you would take the cubed root, You should be able to do that on your calculator. If you need help, I can probably show you, but you probably have a cube root function or at least some kind of, yeah, it depends on your calculator, but you should be able to find your cube root function. Let me know if you need help with that. So then this way you're going to get x, and then you're going to have to use x to answer the problem. So whatever the question actually asks for, determine the hydroxide ion concentration. Okay, so remember, hydroxide ion concentration is actually this 2x. So once you get your x value, you have to multiply it by 2 to get the actual concentration of this ion, okay? So when we have compounds that are not a simple 1-to-1 ratio in their formation, you have to adjust your unknowns, your variables in those calculations. Okay, so 22, let's take a look at 22. 22A, okay, 22A is the same as all the other questions you've done, so that's no problem. But let's take a look at 22B. 22B is an example of this type. So 22B, let's do that one together. So the KSP values from table 3, we still have to look at those. We'll grab those. But we're looking for the KSP value for CaF2, and we're trying to find the concentration of F. So the first thing I do is to write the dissociation equation so that I can see what ratios I have. So CaF2, that's going to dissociate to and become in phase equilibrium with Ca2 plus, because that's the ion that calcium makes, plus 2 F minus ions, because minus 1 is the ion that fluorine makes. So this is our dissociation equation. A good idea to throw the 1s in there so you can see what's going on. And the KSP is built from the concentrations of the ions multiplied together with the appropriate exponents. So this is, first of all, this is going to be a 1, so that's a 1x, and this is going to be a 2x. So there's going to be twice as many fluorine ions that are going to be produced when this dissolves. You see this splits up? We're going to have 1 mole of calcium ions, but we're going to have 2 moles of fluorine ions being produced. The KSP expression, which also you should make sure you note, especially when you have a situation like this, is going to be the concentration of Ca2 plus to the power of 1 times the concentration of F minus to the power of 2. And it's from here that we go ahead and start inputting our values and our unknowns and so on. So CaF2, did you guys find that on that previous page? Let's see, fluorides, hydroxides, what? CaF2. What, PbF2? Okay, CaF2, 3.5 times 10 to the negative 11, you see that? So we've got 3.5 times 10 to the negative 11, and that's got to come from x here for the Ca2 plus times 2x squared. Okay, now just an aside, if this was a 1 something plus 3 something ion, right? If it was something like that, then guess what? This would be x and 3x. Then you'd have x times 3x what? Cubed, right? You see that? So whatever this is, that affects this and this. So we have a 2x here and a squared. So if we take this along, let's see, let's go back to blue. So I've got 3.5 times 10 to the negative 11 equals, this is going to be 2x times itself is 4x squared. Times x is 4x cubed. Okay? We're going to divide both sides by 4, and then we're going to take the cubed root. Okay? And so that's how we're going to get, that's how we're going to get x all by itself. So the cube root and the cube go, the 4 divided by 4 go. So we just have x left over here. So let's take a moment to see what we get here. So I'm going to do 3.5 times 10 to the power of negative 11. I'm going to do divided by 4 first. Okay, so I get this number. Now the cube root, I think with this calculator, it's in the math function. You might have a x to the 1 over y. That might be your function. If you just have a x to the y, a power button, you can do power of bracket 1 divided by 3. Remember? So the cube root is the same as taking something to the exponent of 1 over 3, so a third. You can do that too. I'm going to use this cube root function here on my calculator. I'm going to do cube root of my answer. So I get 2.06 times 10 to the negative 4. There's only 2 sig figs in my question, so I guess if I was having to figure out how many decimal places I go, I'd probably just go 2.1, right? So x is 2.1 times 10 to the, what did I say, negative 4? Negative 4. Now, is that what I'm asked for? Well, it's right now it's just an x. You haven't answered any question yet, right? So what is the question? What's the F concentration, the fluoride ion concentration? So guess what? I need, the fluoride ion's concentration is represented by 2 times x, right there. Not 2x squared, but 2x. So the concentration of F minus is equal to 2 times 2.1 times 10 to the negative 4. And so we simply go ahead and times 2 there, and we get 4.2, yeah, okay, so, well, yeah, don't round until the very end of the question. How about that? So I rounded here. This would be 4.2 if I did this, but it really should just be still 4.1. So there's a little hesitation there. Please don't round too early in the question. Just round at the very end. So leave all your decimals like I did. So this is actually going to be 4.1 times 10 to the negative 4. Right? Okay. So let's see. Let me see if we have. What question was that? That was 22B. Okay, 22B. So 22B, let's see. Okay, so S and 2S. Okay. 4.2 times 10 to the negative 4 molar. There you go. Now they showed their work just a bit differently, but it's no big deal there. Okay. There's your answer. Any questions? All right, finish 22, 23, and 24. That's going to be our, well, that's going to be this lesson for the day anyways. Any questions that you guys have?